very warm welcome to everyone joining us for the Distributed SQL Summit 2024. Good evening, good morning, good afternoon, depending on where you're joining us from. We really hope you're enjoying the session so far. I'm very pleased to have Josh Levinson with me on the call. Josh, would you like to introduce yourself real quick?
Yeah, thanks, Reyes. Hi, everyone. My name is Josh Levinson. I'm a principal product manager at Amazon Web Services, and I'm also known as one of our resident time nerds at AWS. So very excited to speak on this topic and share more with what we have and what Yugabyte and Shreyas and team are building.
And we are very excited to have you, Josh. I'm Shreyas Agnihotri. I'm on the product management team here at Yugabyte. And we have a very interesting topic to talk about today, and it's about time. So let's get started. The topic for today is related to time synchronization in distributed systems and how we are pushing the envelope together, Yugabyte and AWS. So before we go further into the topic, here's a little overview of what to expect in this session. We're going to cover how clock sync works in the distributed world and some of the related challenges, how it affects the DB performance, and then how Amazon Time Sync service is making life better for everyone building a distributed system. And we are very excited to talk about some of the results we have been able to unlock by working together with Amazon here. So without further ado, let's launch into clock sync in a distributed world. So before we talk about the distributed world, let's see how clock sync looks in a monolithic world where you just have a single node system, maybe a database, and it's just one node. So on the right-hand side, I have the reference clock, which could be an NTP clock. And then we have one node on the left-hand side, and you essentially have the timestamps going from 80 to 120, right? Just as an indicator. And even if the actual clock on this particular node is off from the reference clock by a few ticks, you still don't have to deal with any ordering issues. So let's imagine that there are two statements being applied or issued on this particular database node. One of them is an insert statement. Let's say we are inserting some values in a table. And then the other statement is a select statement, which essentially selects all the values from the table and displays them. So in this case, even if the actual clock or the system clock on this particular node is off from the reference clock by a few ticks, we are not going to have any ordering issues. It's still going to execute the insert first and then the select. So the select will reflect the values that were inserted by the previous statement. So life is simple in a single node in a monolithic world, but it really gets complicated as we move towards a distributed world. In this case, you have three different nodes, N1, N2, and N3. And as you can see, each one of them has a different system clock, and each clock is going to be off by a few ticks just due to the clock drift. And as you can see, node 1, as compared to the reference clock, is slower than 10 ticks. Node 2 is slower than 20 ticks. And in this case, node 3 is actually faster by 10 ticks as compared to the reference clock. So how it affects the ordering in this particular case is, let's assume that the insert statement was sent to node 3, N3. And because the node N3 is running faster, it gets recorded with the timestamp of 110. And then let's imagine that the select statement was subsequently sent to node N2. Because this node is running slower than the reference clock, the timestamp for this particular statement gets recorded as 80. Now, if you were to look at the ordering here, we essentially see that the select statement gets executed before the insert statement, and it's not going to have the updates which were inserted as a part of this insert statement, which is not what we expect, right? So how do you deal with this synchronization problem when the clocks across different nodes in a distributed system are not in sync with each other? This is essentially what we just described, right? So distributed systems are designed to run across multiple nodes. In some cases, it could even be across different geographical regions. And since we cannot perfectly synchronize across multiple nodes, there is going to be clock skew. We need perfect ordering to establish the causal relationships between different events happening across these nodes, which is the problem we just described. And then there are some solutions which have been proposed for this, like logical clocks or Lamport clocks. These are just monotonically increasing timestamps, which solve the ordering problem, but then they do not track physical time. So sometimes you also want to know the physical timestamps for the events. So it's not really an acceptable solution from that perspective, unless you use some central time authority. And central timestamp authority is not a feasible solution either, because in that case, the central timestamp authority or the timestamp oracle can become a single point of failure, or it can even become a scale bottleneck due to the latency issues. So is there a better way? Can we synchronize in a distributed system without sacrificing either of the two? So there is a solution which combines the benefits of both physical clocks and logical clocks, and that's the solution which Yugabyte has chosen. It's called a hybrid logical clock. Let's quickly go over what a hybrid logical clock is. It combines the benefits of a physical clock with those of logical clocks by combining the physical wall clock value with a monotonically increasing logical component. The physical part of it is synchronized using NTP. And the second part, which is a logical counter, it's basically incremented by the database itself. Now, YugabyteDB nodes, whenever they are exchanging any messages with each other, since YugabyteDB uses Raft as a consensus protocol, if there's any exchange of Raft messages, if there's a heartbeat, or if there's a leader election that happens, or we are simply replicating data. In all of these cases, YugabyteDB nodes are going to update the HLC, and that looks something like this, right? You have a physical component, you have a logical component, and together it forms a 64-bit value. So the hybrid logical clock essentially solves the problem in an elegant way, and it provides you an ordering across distributed system despite clock skew. So it adds tolerance to clock skew across different nodes, but then there are some trade-offs that come with the clock skew. So let's take a look at what are the associated trade-offs. The typical trade-offs are related to the database performance itself. So if you have higher clock skew in the system, it essentially means there's a bigger uncertainty window. To ensure consistency, YugabyteDB might have to retry the transaction so that we preserve the strong consistency. And then if there are higher number of retries, that typically leads to a higher latency, right? So essentially higher clock skew equates with higher latency. And by default, YugabyteDB uses a conservative value of max clock skew. This is the maximum clock skew between any two nodes in the YugabyteDB cluster. The default value is set to 500 milliseconds. And this is the upper bound. This is not necessarily the clock skew that you see between two nodes at any given point, but this is the maximum value that we allow. And with typical NTP, this can be in the range of anywhere from 1 milliseconds to 100 milliseconds. So this is really a conservative value. So this also acts as an uncertainty window. If we detect that there's any conflicting writes happening to the same key or the same record in the database within this uncertainty window, then to ensure consistency, YugabyteDB has to restart the transaction. So going back to our previous example, if you see, we first got an insert statement, which went to node 2, and then there was a select statement, which went to node 1. Now, if these two happen, and they're updating the same value here, if both of those statements fall in the uncertainty window of 500 milliseconds, then what YugabyteDB is going to do is it's essentially going to retry that select so that we can ensure consistency, right? So that allows us to make sure that the insert statement is taken into consideration by the select. We made a bet in 2016. We made an assumption that clock synchronization in public clouds is going to better over time, and that's exactly what is happening now. So bingo, we see that accurate time is now accessible for everyone thanks to Amazon's time sync service. And at this point, I would like to invite Josh to tell us more about how Amazon time sync service is democratizing accurate time for everyone. Go for it, Josh.
Thanks, Shreyas. Yes, very excited about using wall clock time and combinations like hybrid logical clock time within Yugabyte. And something we're also looking at and doing within Amazon Web Services. So at AWS, we took a step back, looking at what customers and partners like Yugabyte are doing, what other customers are doing, what our own teams are doing. And we saw the difficulty, the extra work, the retries, the additional network packets and transactions you need to do on your nodes on any distributed application when you can't look at wall clock time. And instead of looking at that and assuming that that is a moving forward standard, we took a step back and we said, well, what if clocks were actually better? What if they were reliable? What if you could use them not just for entertainment and for time saving, but actually use them as a feature, not a bug, in a distributed system? So in doing that, we looked at, okay, what do we need to measure in a distributed system? It could be a network packet going around the world. So we'll say, California to Europe and back. SSD reads, but more importantly, with someone like Yugabyte or a distributed system, you're looking at not just across regions or across availability zones, but even within a single data center or within read writes in memory locally on a server or an application. And so we looked at this and saw, okay, we really need to be in the low microsecond range, setting a target of around 20 microseconds, so that you have a better ruler with which to measure the transactions. When you're in multiple milliseconds, either way within your clock skew, you really can't look at those data center round trips or their memory reads to order things. And that results in the large number of retries and the extra work. And it ends up being in either delays at best for customers reading and writing data, but at worst, the danger of getting your transaction ordering wrong. So what we did at AWS is, instead of looking at just NTP or PTP, we saw that those were not going to get us into the low microsecond range of clock accuracy, and realize you need to be on the reference clock. The biggest cause of error in your clock is your actual network itself. And then as you scale and you have a bigger network across multiple data centers, multiple regions, it gets more and more difficult to keep your clocks in sync. And all of these applications are as good as their worst clock, not their best, because you add the skews together and need to assume the worst case scenario, as Shreyas pointed out earlier. So what we've done is we've made an investment in hardware to make every Amazon EC2 instance a reference clock, essentially from NTP speak, making everyone a Stratum 1. We have a Stratum 0 reference going to every EC2 instance. And this is over dedicated infrastructure. So we have multiple antennas, multiple atomic backups, dedicated hardware cabling going directly to the Nitro system and the Nitro card on our EC2 instances in order to provide that hardware reference clock to keep the skew as low as you can. In this photo is one of our timekeeping appliances showing the Nitro system and the FPGAs that we use. Again, it's all hardware based, not software based, to give customers the best time that we can, all the way into the guest OS and application. Of course, that's just the hardware component. And as Shreyas pointed out, you need to get all the way into software. And one thing that we are firm believers of is assuming the worst case scenario. Again, your application is good as its worst clock. So we prefer to talk about the clocks in terms of the clock error bound. Your clock error bound is a 100% confidence interval, the P100 of where your clock could be. So when we say we're delivering a clock error bound of 20 microseconds, the reality is your clock is most likely much better than that. You're in the low microseconds and nanosecond range. But for an application, you need 100% certainty that you're right. You can't estimate, you can't be right half the time, 90% of the time, 99% of the time. You need a true guarantee when you're basing your transaction order and the security and correctness of your customer data. And so that's how we look at the clock error and how we recommend our customers and partners to look at clock error. But of course, doing that is a lot of work. You not only need good clocks underneath the system, but you need a way for your software and your application to see and look at the clock error in real time. Next slide, please. So what we did was we built a tool that we call ClockBound that looks at the clock error for you. We built this in Rust and C. We've open sourced it. We use it ourselves. We've shared it with partners like Yugabyte. Anyone can look, download, use this software as a reliable method to compare and order timestamps across nodes or hosts in your application. It gives you an audit if your clock is connected through your NTP daemon. And it allows you not just for logging and tracing events, but also comparing a current event or process to previous timestamps. And the real power here, as Shreyas pointed out, is not just looking at one node, one application, but looking at multiple nodes, multiple hosts. And it doesn't need to be the same data center. It could be across availability zones, even across regions and geographies around the world. And it doesn't need to be used on AWS specifically. But the key is, of course, having infrastructure underneath, clocks that you can trust. If you don't know how good your clocks are, if you can't trust them, if you can't trust your hardware running, maintaining, backing up, ensuring that your clock is correct, then you can't assume the output in your software is correct. But all of that said, we feel it's very important to keep this open source and to keep this available for any customer, any service, any application to be able to use clocks as a primitive. And again, turn clock skew from being a bug to being a feature in a distributed system.
Well said, Josh. And we would really like to give a shout out to Amazon for making this open source. We are an open source company as Yugabyte, and we really value Amazon contributing to the open source world and especially making it available on different hardware. But the real value is in making sure that the underlying infrastructure can provide you microsecond accurate time. So with that, Josh, let's see some of the results that we have been able to unlock together with this collaboration.
Yeah, excited to share.
Yeah, absolutely. So before the big reveal, I would like to say YugabyteDB is essentially using Amazon's AWS ClockBound library. And since it gives us the clock error with respect to the reference clock, we are able to use that additional information in a way that reduces the uncertainty window, right? So I earlier talked about we allow the max clock skew to be 500 milliseconds, with very accurate hardware which uses PHC, and combining that with the clock error which is supplied by AWS ClockBound library, we are able to reduce this uncertainty window quite a bit in microsecond range rather than 500 millisecond range. And if you compare the left-hand side here, which is the max skew possible, right? So this is the worst case possible, which has 500 milliseconds worth of clock skew between two nodes in a cluster. And in this case, Yugabyte is still using the hybrid logical clock to tolerate that clock skew and be able to give you strongly consistent results despite the clock skew. So that's the left-hand side. And if you compare that with the right-hand side, which is now using microsecond accuracy in the range of 50 microseconds with Amazon EC2 instances, with the Nitro hardware that Josh was talking about with PHC enabled. Now, YugabyteDB has been able to enhance our hybrid logical clock to a new kind of architecture, which we call as dynamic hybrid logical clock. And the way it operates is it fetches the max clock error dynamically using the ClockBound library. And we are able to reduce the uncertainty window by the virtue of that. So with that, we see 3 times reduced latency. So essentially, your transactions complete faster. We see twice as much throughput as before. And then because the uncertainty window has shrunk so much, we see 1,000 times fewer transaction retries. So if you remember the slide from before, it basically means much faster latency for your applications. And obviously, this comparison is between the worst case and the best case. So your mileage may vary. It's going to be somewhere in between. But it's still a significant gain due to the fact that Yugabyte can use the clock-bound library to implement the hybrid logical clock in a better way.
I'm very excited about this, and I do want to highlight the thought and the intelligence that Yugabyte are doing instead of taking a static clock and looking at a dynamic hybrid logical clock. Even with our better clocks in the microsecond range, it's not a fixed accuracy, and it's quite dangerous to assume that your clocks are perfect or fixed, even in a tighter balance. And so what Yugabyte's doing, which is really smart, is they're taking the clock in real time, looking at that P100 confidence of the clock error and adjusting accordingly. That way they can ensure correctness and consistency as they go through.
Yeah, absolutely, Josh. And just one additional data point here that these tests were run on Amazon EC2 instances using a simulated workload, which is linked in the slide. It's also available as a GitHub repository on YugabyteDB GitHub handle. So it's called YB Sample Apps, and we'll be sharing more details on our blog, which will come out soon after this on how to replicate some of these results if you want to try it out in your own environment. So how do you try this, right? That's the next question on everyone's mind. So this is available as a tech preview feature with YugabyteDB version 2.23.1, which is our preview release. Or you can also use a stable version, which is 2024.2 to try out this feature. It's gonna come out very soon. And we are welcoming design partners for this feature. Please try it out, provide us your feedback on YugabyteDB Slack community. Again, kudos to Amazon for making the cloud-bound software open source, and it's definitely going to help the ecosystem in general. And we hope that the collaboration will continue and things will continue to get better from here. So with that, we are at the end of this presentation. We thank you for your time today. We hope that you found some of this information useful. If there are questions, please leave them in the chat here. Josh and I would like to answer your questions, as many of them as possible in this session. If there are some questions we are not able to answer during this session, we'll definitely answer them offline. So thanks for your time again, and thank you, Josh, for such a wonderful collaboration.
Thanks, Reyes. Thanks, everyone.